Astronomers have determined what caused the most powerful gamma-ray burst in history. In October 2022, observatories around the world recorded the strongest gamma-ray burst in history. Using the James Webb Space Telescope, JWST, astronomers determined that the flare was caused by a supernova, but during their research they encountered further puzzles. On October 9, 2022, for 7 minutes, high-energy photons from a giant explosion more than 2 billion light-years away shook the Earth's atmosphere. This event, called a gamma-ray burst, GRB, was dozens of times brighter than the previous record holder and was named by researchers BOAT, short for the brightest of all time. In addition to the light show, this explosion also ionized atoms in the upper atmosphere. If a similar explosion occurred closer, it could potentially harm life on Earth. Astronomers weren't entirely sure what caused this GRB, designated GRB 221009A. These types of explosions glow as intensely as a bright star in the Milky Way, even though they are billions of times more distant. To throw so much energy across billions of light-years, GRBs must be really powerful. Astronomers believe that some of these explosions may come from supernovae, i.e., exploding stars that have come to an end and collapsed into a neutron star or black hole. The new findings, made with the help of the James Webb Telescope, indicate that the source of the explosion was a type of supernova called a collapsar, a massive, rapidly rotating star that ran out of fuel collapsed, throwing its outer layers into space before disappearing into a black hole. The extreme conditions in the collapsar should allow the production of the heaviest elements found in nature, such as uranium, platinum and gold. Given the brightness of the explosion, scientists expected to find traces of these elements in the star's ashes. However, no such thing was noticed. The results and description of the research were published in the journal, Nature Astronomy. When we confirmed that this GRB was formed by the collapse of a massive star, it gave us the opportunity to test our hypothesis about the formation of some of the heaviest elements in the universe, said Peter Blanchard of Northwestern University, who led the study. But we saw no heavy element signatures, suggesting that extremely energetic GRBs like BOAT do not produce heavy elements, he added. The powerful explosion occurred at a distance of approximately 2.4 billion light-years from Earth, in the direction of the constellation Sagittarius, and lasted several hundred seconds. Astronomers were surprised by the power of the phenomenon. The event emitted the highest energy photons ever recorded by satellites designed to detect gamma rays, Blanchard said. It was an event that the Earth sees once every 10,000 years. We are lucky to live in a time when we have the technology to detect such flares occurring throughout the universe. Observing such a rare astronomical phenomenon as BOAT and research to understand the physics behind this unique event is extremely exciting, he added. Astronomers had to wait a while before making observations. It was only about 6 months after the incident that JWST turned its watchful eye on the source. The GRB was so bright that it obscured any potential supernova signatures in the first weeks and months after the explosion. Shortly after the incident, the GRB's glow resembled the headlights of a car driving straight at you, making it impossible to see the car itself. So we had to wait for it to weaken to give us a chance to see the supernova. Blanchard said. Researchers used the near-infrared spectrograph at JWST to observe the object's light at infrared wavelengths. That's when they noticed the distinctive signature of elements, such as calcium and oxygen, typically found in supernovae. Surprisingly, the supernova itself didn't turn out to be particularly bright, so why was the GRB that accompanied it so incredibly bright? It looks quite normal in the context of other supernovae associated with less energetic GRBs. The same collapsing star that produces a very energetic and luminous GRB can be expected to also produce a very energetic and luminous supernova. But it turns out that's not the case, Blanchard said. After confirming that BOAT it was the result of a supernova, and Blanchard and his colleagues began looking for evidence of heavy elements in its remnants. Astrophysicists have an incomplete picture of all the mechanisms in the universe that can produce elements heavier than iron. The basic mechanism for producing heavy elements is the so-called R process, rapid neutron captures process. So far, astrophysicists have only confirmed the production of heavy elements through this process when two neutron stars merged, a collision detected by LIGO in 2017. But they say there must be other ways to produce such elements. There are simply too many heavy elements in the universe and too few neutron star mergers. In addition, neutron star mergers are too rare to be the main source of heavy elements. There is probably another source. Neutron stars take a very long time to merge. However, observations of very old stars indicate that some parts of the universe were enriched with heavy metals before most neutron stars had time to merge. This shows us an alternative channel. Blanchard said. Astrophysicists have hypothesized that heavy elements could also be created by the collapse of a rapidly spinning, massive star. Exactly the type of star that generated BOAT. Different elements absorb and emit photons of different wavelengths, depending on their atomic structure, giving each element a unique spectral signature. Therefore, looking at the spectrum of an object can tell us what elements are present in it. After examining the spectrum of BOAT, we observed no heavy element signatures, suggesting that extreme events such as GRB 221009A are not primary sources. This is crucial information as we continue to try to determine where the heaviest elements are created, Blanchard explained. To distinguish the light from the supernova from the bright glow that appeared before it, researchers combined the JWST data with observations from the Atacama Large Millimeter, Submillimeter Array, ALMA, in Chile. Combining data from both telescopes helped us accurately measure the brightness of the afterglow during JWST observations and allowed us to accurately isolate the supernova's spectrum, said FNk9Y. Lasker of the University of Utah, co-author of the paper. Although astrophysicists have yet to discover how the same star produced a normal supernova and a record bright GRB, Lasker said it could be related to the shape and structure of relativistic jets. Rapidly rotating massive stars collapse into black holes, producing jets of material that shoot out at nearly the speed of light. If these streams are narrow, they produce a more focused and brighter beam of light. It's like focusing a flashlight. In fact, it was one of the narrowest jets ever observed in a gamma-ray burst, giving us a clue as to why the afterglow appeared as bright as it was. Other factors may also be responsible for this. Scientists will study this issue for many years, Lasker admitted. multifractal brain and the early stages of multiple sclerosis. Brain electrical signals in patients with multiple sclerosis, a disease associated with slow information processing and lack of motor coordination, show traces of multifractality. Scientists from 4 Polish research institutions have found multifractal analyses of electrical signals flowing from the brain can help in early determination of the severity of the disease, demonstrated by scientists implementing the biologically inspired neural networks project. The study involved experts from the Jagiellonian University, UJ, Kraków University of Technology, SWPS University, USWPS, in Katowice and the Institute of Nuclear Physics of the Polish Academy of Sciences, IFJ-PAN, in Kraków, where multifractal analyses were carried out. At the stage of fractal analysis, specialists from IFJ-PAN noticed that electrical signals flowing from the brains of healthy people show certain long-range trends, which makes the graphs of their electrical activity visually smoother than those of patients with multiple sclerosis, whose brains send more jagged signals. But when multifractals are involved, the situation changes. The electrical signals emitted by the brains of healthy people are less complex than those of sick people. In people with pre-developed multiple sclerosis, communication between neurons is more complex. However, neurons are not fully independent of each other, because they are still jointly responsible for generating the EEG signal. And that is why we observe a convolution of fractals, i.e. multifractals. In turn, in the case of the control group, with healthy people, individual fractal components are more regular, fit together better, and the multifractal structure becomes more difficult to notice, said the co-author of the work, Dr. Hab, quoted in the press material. Paweł Oświęcimka from the Department of the Theory of Complex Systems, IFJ-PAN. The interpretation of the obtained results was presented by Professor, Ph.D. Tadeusz Marek from the Faculty of Psychology, USWPS. The presence of complex signal organization in people suffering from multiple sclerosis may indicate compensatory processes taking place in the brain's neural networks. The brain tries to compensate for the deficit resulting from the disease and looks for ways to bypass the damaged areas, which leads to the reorganization of the network. The functions of these areas are trying to be taken over by other groups of neurons that are still working effectively, which is reflected in the increase in the complexity of electrical activity, said the professor. Summarizing the results of the analyses of multifractal EEG recordings, Marek emphasized that they turn out to be a highly sensitive tool that allows for the detection of compensatory processes occurring in the brain's neural networks in the early phase of the development of multiple sclerosis. Multiple sclerosis is an incurable disease leading to degeneration of the central nervous system, manifesting itself in motor and sensory disorders. Its course can only be mitigated, the more effectively the earlier the disease is detected. The research participants were selected by scientists and doctors from the Department of Neurology of the Jagiellonian University Medical College and the Department of Neurology of the Jagiellonian University Hospital. The group with diagnosed, pre-developed multiple sclerosis was ultimately reduced to 38 people, and the control group to 27. Electroencephalographic (EEG) data were collected several times over 2 years, each time engaging the subjects in different tasks. Brain electrical activity was measured using 256 electrodes sampled 1,000 times per second each. Before the actual analysis, the signals were cleaned, for example by removing eye blink effects. They were grouped into groups corresponding to 20 brain areas. The total amount of collected data is so large that it will take our team years to complete a full set of multifractal analyses. Therefore, the article that we have just published in the journal, Biomedical Signal Processing and Control, discusses only the readings collected during the earliest phase of measurements. Regarding the situation when subjects taking one of the 2 prescribed pharmaceuticals did not perform any activities during the measurements, says Dr. Hab. Auschwitz. He added that searching for multifractal relationships is computationally demanding. Such work has become popular only in the last dozen or so years. Along with the increase in computing power of computers and the development of software. As a result, in many areas of scientific activity, multifractals are only at the stage of taking the first steps. One of such areas is the analysis of the complexity of electrical signals emitted by the human brain, especially in the context of degenerative changes occurring in it, explains Dr. Hab. Auschwitz. He explains that the basic feature of ordinary fractals is their self-similarity. If we enlarge them, sooner or later we will see a structure very similar to the initial one, or even identical. However, when we combine several fractals, the result will generally be noise. However, there are mathematical operations that weave fractals into complex structures that retain the ability to be self-similar. However, in ordinary fractals, self-similarity is revealed when we scale their free fragment by a factor for a given fractal, which is always constant, while different fragments of multifractals must be scaled in different ways. This feature means that while analyzers using ordinary fractals allow us to detect linear relationships, for example trends, multifractals can reveal the existence of less obvious nonlinear correlations. Currently, a survey, which is very subjective in nature, is used to assess the advancement of multiple sclerosis development in patients. More objective tests require the use of magnetic resonance imaging, so they are not only invasive, but also highly costly. According to the team of scientists, discovering the relationship between the patient's condition and the multifractal complexity of his brain's electrical activity would allow for an objective assessment using a non-invasive measurement technique that is not burdensome for the patient and is easy to use. The results described in the article are the first phase of analyses of EEG signals collected during the discussed scientific project. The remaining electroencephalographic data are being processed. The scope of the research was broader and also included brain imaging using structural and functional magnetic resonance imaging techniques. The result is a series of photos showing cross-sections, based on which it is possible to reconstruct the structure of the brain and changes in blood supply and oxygenation of its various areas. The search for multifractal harbingers of multiple sclerosis will therefore continue, not in one, but in 4 dimensions.